This video gives an example of working a projectile motion problem, and in this problem we're going to launch at ground level and land at ground level, so there's no cliff type aspect to this problem. Launching and landing at the same vertical distance from the center of the Earth. We have a ball that's somehow launched at 24 meters per second, and the angle for the initial velocity 67 degrees from the horizontal. The question is, how far does it travel before impact in the horizontal direction? How far away from the launch point will the ball hit the ground? So we know that in projectile motion, when we ignore air resistance, the acceleration in the x direction is 0. So the velocity in the x direction is a constant. The component of the velocity in the x direction is a constant. We can use distance equals rate times time. We are given the initial vector, 24 meters per second. We're given the angle, so we can easily find the component in the x direction using the cosine function to help with that. We're looking for the adjacent side to the 67-degree angle. You might want to draw your own little right triangle, and 24 meters per second would be the hypotenuse. Cosine of 67 degrees multiplied by that produces 9.378, keeping an extra digit here just to avoid round-off error. But that's the meters per second in the x direction. The time in the air is still a mystery. To get the time in the air, we're going to use the vertical part of the problem, and we're going to work the problem just to the top of the motion. And at the top of the motion, having that time, again ignoring air resistance, the time to go up equals the time to go down, so the time in the air is double the time to go up. So time for us to start investigating the y equations. To use the y equations, the acceleration due to gravity is in the vertical direction, the y direction, I'm calling it. We must have a velocity in the y direction from the launch velocity. It is illegal to use the 24 meters per second. That 24 meters per second is not vertical. And in our equations, we have to only use numbers that are parallel in direction. So the y equation here has an acceleration that's vertical. We need the initial component of the velocity in the vertical direction. And of course, the sine function enables us to calculate that. Again, refer to the right triangle that you draw. And the side opposite the 67 degrees is the vertical side of that right triangle. And we have 22.09 meters per second in the vertical direction. That's the initial y velocity. At the top, for an instant, the y velocity is 0. So that's going to be our stopping point for our calculation. Well, equation 1 can easily be used to produce the time to go to the top of the motion, the time up, I'll call it. So we have 0 for the final velocity at the top of the motion. Temporarily, the object's at rest in the vertical direction at the top. Remember, it still has the x motion, but this is only a vertical problem. We're only interested in what's happening vertically. So at the top of the motion, 0 meters per second. Our initial vertical motion is the y component, 22.09 meters per second. Our acceleration is negative. I'm working this problem with up being the positive direction. And then we have time up over here. So the time up is 2.254 seconds. And we can then continue this and calculate our total time in the air just by doubling the amount of time that we are working with to go up. So if we double that, and I'll scroll down a little bit here hopefully, we find the time in the air is 4.509 seconds. Well, we're ready to calculate. The range is the rate in the x direction that is a constant when we ignore air resistance. So that is the x component of the initial velocity, 9.378. We multiply by the time in the air, and we produce the range, and I'll round off to 3 decimal digits here, or 3 significant figures. The object lands 42.3 meters away from the launch point. So we were asked to calculate the range. The range involves the x velocity component multiplied by time in the air. The x velocity component was found by using a right triangle and finding the component of the initial velocity in the x direction. That's how the cosine was brought in. We have that x component, and then the y motion provides the time to go to the top of the motion. We double that and we find the time in the air. So practice, invent your own little problem, practice and see if you get some reasonable result. Ask questions.